Hello everyone, and welcome to Geometry Lesson 3-4, Perpendicular Lines. In this video we're going to talk about perpendicular bisectors and some theorems that are involved in perpendicular lines. So let's start by looking at what a perpendicular bisector is. So the words perpendicular and bisector should be familiar. A bisector cuts something in half, and perpendicular means it meets at a right angle. So a perpendicular bisector is a line that's perpendicular to a segment at the segment's midpoint. So it hits the midpoint in a right angle. Now, the shortest segment from a point to a line is perpendicular to that line. So you may have heard it said that the shortest distance between 2 points is a straight line. It's kind of what this is saying. So if you want the shortest segment, look for the one that is perpendicular to a line. Okay, so let's take a look at an example where we have to identify a shortest segment and then write an inequality and solve it to find the measurement that x could possibly be. In example 1, it asks us to find the shortest segment from point P to line AC, and it gives us this picture. And point P is here, and AC is down here. And then it also asks us to write and solve an inequality for x. Now for this first part, the shortest segment from point P to AC, notice you look from point P, there are 3 segments, PC, PB, and PA. Look for the one that has the perpendicular symbol. That's going to be the shortest segment. So PB is the shortest segment because it is perpendicular to AC. Now, when we write and solve an inequality for x, notice PB was the shortest segment, which means that 5 is going to be less than this expression here. So I'm going to write that in an inequality, and then I'm going to solve for x. So I wrote my inequality that 5 is less than x plus 3, and then I subtracted 3 from both sides to get 2 is less than x, or x is greater than 2. So that's how you would write and solve an inequality. Now I have a question for you guys to try. It works exactly the same way. So try this question and then see if you got it right. In Check It Out number 1, they gave us this diagram here. And in part A, they said, what is the shortest segment from point A to line BC? And then in part B, they said, write and solve an inequality for x. So pause the video and try and do that, and then hit play to check your answers. So for part A, the shortest segment would be segment AB, because here's point A, and the one that's perpendicular to the line is this one right here, so it's AB. So that's our shortest segment. Now to write and solve an inequality, I took the measure of that short segment, and I made it less than the other measure that was given. So I got x minus 5 is less than 12. Now I just added 5 to both sides to get x is less than 17. So the next thing that we're going to look at are some theorems related to perpendicular lines and parallel lines. Now notice that I have 3 theorems here. Only one of them has a specific name. The other 2 are not the most used theorems that we have. So what they've done is they've given us some abbreviations to use to relate to them in a proof. So if I need to use this theorem in a proof, I can either write out the whole fact, or I can use this abbreviation to state the fact. Now, these numbers that are given are specific to the book that I use, so those numbers don't really mean anything to anyone outside of my class. So our first theorem, it says if 2 intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So that uses a lot of very specific knowledge. Linear pair are 2 adjacent angles that form a straight line. So notice they form a straight line. That means that these 2 angles have to add to 180 degrees. They're supplementary. And those 2 angles are also congruent. And if they're congruent and they add to 180, then they're both going to be 90 degrees, making this line perpendicular to that line. So our conclusion is that those 2 lines are perpendicular. The next theorem is what we call the Perpendicular Transversal Theorem. So it says in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. That means if I know these two lines are parallel, and I happen to know that this is perpendicular right here, then I know it's going to be perpendicular down here because, notice, those are corresponding angles. And if my lines are parallel, which they are, corresponding angles are going to be congruent, which means that this is also going to be 90 degrees. This is just a shortcut to getting there, so you don't have to use the corresponding angles theorem. You don't have to substitute in measures. It just tells you that if you know it's perpendicular, you can take the shortcut and say that this angle here is also going to be perpendicular, also going to be 90. So this line down here and this line right here are going to be perpendicular. The final theorem says if two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. It's kind of like the converse of this previous one. So if I know that these two are right angles, and I know that this hits both of these other two lines, then I know those other two lines are going to be parallel. Again, think about corresponding angles. Our corresponding angles are both 90 degrees. They're both congruent. So using the converse of the corresponding angles theorem, we know that these two lines are going to be parallel. So we're concluding that the lines are parallel. Okay, so we're going to take a look at an example, which is a proof where we're going to apply some of these theorems. In example 2, it asks us to write a two-column proof. It says given line AD is parallel to line BC, line AD is perpendicular to line AB, and line BC is perpendicular to line DC. Notice in the diagram, they've given us all of that information. We have our parallel lines here, we have one of our perpendicular lines right there, and the other one down here. And they want us to prove that AB is parallel to DC. So I recommend pausing the video, trying to do that, and then hit play to see if you're right. In my proof, I started out with the given statement. AD is parallel to BC, AD is perpendicular to AB, and BC is perpendicular to DC. Then, because I know that this line is parallel to this line, and this is perpendicular, I use the perpendicular transversal theorem to say that AB is perpendicular to BC. So that's our perpendicular transversal theorem. Now notice, it's perpendicular here, and it's perpendicular here, so I can use that unnamed theorem that we had to say that because it's perpendicular here and here, then these two lines are going to be parallel. So AB is parallel to DC because two lines that are perpendicular to the same line are parallel. Okay, we have one more example to see. This is an application question. If you've ever been to the shore, this would be a great point of knowledge to have. It says rip currents may be caused by a sandbar parallel to the shoreline. Waves cause a buildup of water between the sandbar and the shoreline. When this water breaks through the sandbar, it flows out in a direction perpendicular to the sandbar. Why must the rip current be perpendicular to the shore? So notice we have the sandbar here, and it's parallel to the shore. And here's our rip current going this way. So they want to know why, if it's perpendicular up here, it would have to be perpendicular down here. See if you can write an explanation and then compare it to the one that I'm about to give. This is an application of the perpendicular transversal theorem. The shoreline and the sandbar are parallel, and the rip current is perpendicular to the sandbar. So that makes it perpendicular to the shoreline. So that's it for this lesson. Let me know if you have any questions.